Hello everyone. This week we're going to cover IP address autoconfiguration. So this week in our coverage of IP addresses and IP address autoconfiguration, we're going to talk about DHCP and DHCPv6 in detail, including IP address management and mechanisms for address delivery, lease and allocation, renewal, and release. After we discuss DHCP and DHCPv6 packet structures and fields, we're going to clarify broadcast and unicast addressing in IPv4, multicast addressing for IPv6. We're going to talk about relay agent communications, and we're going to discuss Microsoft DHCP scopes. Finally, we're going to introduce you to some topics around DHCP and DHCPv6 troubleshooting, give you some tips and utilities. So the objectives for this week, we're going to explain the basic services that DHCP and DHCPv6 offer to their clients and explain its background. We're going to explain the specifics of IP and IPv6 address management using DHCP and DHCPv6. We're going to explain the DHCP discovery, renewal, and release processes. And we're going to explain the basic DHCP and DHCPv6 packet structure and the types of messages that are in use. Furthermore, we're going to describe broadcast and unicast addressing for IPv4, as well as multicast addressing for IPv6. We're going to describe the relay agent communications for both IPv4 and IPv6, and we're going to discuss Microsoft DHCP scopes and classes for IPv4 and differences in IPv6 scope configuration. So although DHCP is considered the most common form of address autoconfiguration, it's not the only mechanism for clients to obtain an address automatically. So Dynamic Host Configuration Protocol, or DHCP, it is the most common, but there's other mechanisms, and these include Microsoft's Automatic Private IP Addressing, or APIPA, and DHCPv6 as well. And we're going to talk about all of these capabilities and their details in this presentation. So we're going to start with DHCP at a high level, and then move into each of the protocols and their specifics. And then also when we talk about DHCPv6, it really is a more robust and controllable system for address autoconfiguration. So Dynamic Host Configuration Protocol, or DHCP. DHCP is a service that provides a way for client computers that lack an IP address assignment to request one from any listening DHCP server without the help of an administrator. So it delivers the necessary configuration to those clients, and DHCP provides hosts with an IP address, a subnet mask, a default gateway, and a primary and secondary DNS addresses. Now, originally, all IP addresses were manually configured and stored on the local machine. So, as networks became larger and more complex, and thin clients became prevalent, administrators really needed to manage the IP address bindings. So, at that point, Reverse Address Resolution Protocol, or RARP, was used so devices could learn their IP address and communicate across the network. BootP was also introduced and implemented for the same reasons, and the origins date back to BootP. That's described in RFC 951, and interoperability between DHCP and BootP is in RFC 1534. DHCP also makes it possible for to administer client IP address assignments and configuration data from a single centralized server instead of administrators having to go from host to host to host to manually configure an IP address. And DHCP servers can also manage more than one range of IP addresses, and each of these ranges is called an address pool. If it's considered as a range of available addresses from which unused addresses can be allocated to clients, or an address scope if it's considered as a range of numeric IP addresses that fall under DHCP's control. And again, remember, the RFCs here that are important for DHCP's definition and operations are 1534, 2131, 2132, and 2241. So how does DHCP work? So when TCP/IP is configured on a client computer, the obtain IP address automatically option is the only necessary element to put in there. When that workstation attempts to access the network, it broadcasts a DHCP address request to the network because it doesn't have an IP address. And all the DHCP servers present on the same broadcast domain get that request and send back a message saying, hey, we're willing to grant an address lease. The client will accept the address lease offer from one of those hosts or servers, and it'll send a packet to that server that extended the offer. And the server will reply to the client with a new IP address. So it proffers an IP address for a specific period of time. That's the lease, and the client uses it thereafter. Now, once that lease expires, so when we talk about that specific period of time, the clients will have to start the process over to either get a brand new address or renew that same lease. Here's an example of the IPv6 properties in Windows, and as you can see, it's marked on here: obtain an IPv6 address automatically, obtain DHCP server or DNS server address automatically. That's basically saying Windows, go out and perform a DHCP request on the network. And the IPv4 properties window is pretty much the same thing in Windows as well. So the idea of leasing, so the role of leases, it's based on the thought that all hosts don't need an IP address for an indefinite amount of time, and they don't need it all the time. And there's probably a limited amount of IP addresses available on the network. And that's going to really be true if hosts are routed to the internet. If you have NAT enabled on your network, you probably have a larger pool of IP addresses, and it's less of a concern in terms of lease timing. But with very large networks and with limited address spaces, leases are a good solution. In the case of internet service providers, while they might own large blocks of routable IP addresses, especially when we talk about IPv4, that supply is finite. So when a client logs onto the ISP and requests an IP address for internet access, the address is assigned for that duration of the lease or the amount of time the host is on the internet. Once that host disconnects, like in the case of a dial-up connection, that address goes back to the pool. But there's a caveat. After a Windows DHCP lease expires, there's a 4-hour grace period where that IP address isn't put back into play. So it can be scavenged, is the term for it, if the pool falls to zero. So lease periods are about 1 to 3 weeks, are typical on networks where machines seldom move and the workforce is stable. But if you have roving workers or mobile workers, it's typically 1 to 3 days. And on ISPs, especially those still doing dial-up or disconnectable connections, it's 4 to 8 hours is typical. So software elements of DHCP, you have the DHCP client. So it's enabled on the client machine when you select the obtain IP address automatically option, as we saw before. DHCP server manages the address pools and configuration data. And the DHCP relay agent, that intercepts the address requests on a local cable segment and repackage those requests as unicast to one or more DHCP servers. Non-Microsoft clients running TCP/IP that are compliant with RFC 2132 can also support DHCP client software. And a DHCP server can also be a domain controller, for instance, a member server, a standalone workgroup server. When you install Windows Server, for instance, you can choose the features and roles on that server, and one of those features is the ability to be a DHCP server. A DHCP relay agent It allows you to place a DHCP client and a DHCP server on different networks. And this is required if you have more than one subnet on your network. Now, as we said before, most DHCP messages are sent as broadcasts. If a DHCP client must send an address request to a DHCP server on another subnet, it has to use a router that's enabled to forward DHCP broadcasts. This is not really forwarding in the true sense of the word, but relaying. And a relay agent doesn't forward broadcasts. It takes a packet, can make changes to it before relaying it to the server on a different network. So, as you can recall from earlier videos and chapter readings, this is necessary when you're routing a packet, because the MAC address of the sending device has to be stripped off and replaced with the MAC address of the router interface sending the packet to the next subnet. So the various types of DHCP leases: there's the manual address lease, where the administrator assigns an IP address manually. There's the dynamic address lease, where the DHCP server assigns addresses for specific periods of time. And then for typical IP addressing schemes, the servers have static IP addresses, the routers have static IP addresses, and the clients will have dynamic IP addresses. In addition to manual and dynamic assignments, the DHCP automatic assignment permanently assigns a specific IP address to a specific client, usually by associating the IP address with the machine's MAC address. Oftentimes you'll see this in consumer routers. So if you log into your own router at home, you'll be able to set DHCP automatic assignment if your home router is providing DHCP for your home network. This can be done without any intervention from the network administrator. So this works best for hosts that are always connected and always on, and the network doesn't suffer from a real shortage of IP addresses. So a little bit more about DHCP leases. How DHCP integrates with DNS. Server addresses are advertised using DNS, and all address updates must be entered manually. So client addresses usually come into play only when email addresses of the form user@domain name must be resolved. DHCP is also integrated with DNS, especially when we're talking about dynamic DNS or DDNS if you've used any of those services. So the DNS database can be updated with a new IP address to name mappings as allocated by DHCP to hosts in the zone. And DDNS updates, they're described in an RFC, and that RFC is 2136. So IPv4 autoconfiguration. There's two types of IPv4 address autoconfiguration mechanisms. The first one is DHCP, and the second one is APIPA, Automatic Private IP Addressing, or APIPA. Most modern operating systems are configured to have their IP addresses automatically provided to them via DHCP from DHCP servers. If a DHCP server does not respond to the host's DHCP request, APIPA is generally configured on the host as a fallback operation to self-assign a link local IP address. So speaking of APIPA, dynamic configuration of IPv4 link local addresses. It's used by interfaces as a failover mechanism to self-assign an IPv4 address if the initial DHCP requests are not answered. However, a network interface will continue to send DHCP requests approximately every 5 minutes. If a DHCP server subsequently replies with an IP address assignment for the host, the APIPA address is released from the interface in favor of the DHCP provided address. So, for instance, you take a Windows machine, if you plug it into a network and you have some problems with it, you've probably seen the 169.254 address scope on that machine, getting some address. That is APIPA. That's what we're talking about here. And the value of APIPA is to allow hosts to communicate on the local link of the network, but that address will not allow routed communications to hosts on other networks. So DHCP again. DHCP discovery occurs when a DHCP client broadcasts a request for an IP address, and that relies on an initial DHCP broadcast. A DHCP server pings an address before it offers that address to the client. The DHCP client broadcasts gratuitous ARP packets to determine if an address is already in use, and a DHCP server blocks that address from being assigned again and offers the client a new IP address. When a DHCP client has no IP address, so if it's booting for the first time or if its lease expires, it must broadcast a request for an IP address to obtain one. This initial activity is called DHCP discovery. DHCP servers hear the discoveries and offer an IP address back. Now, the default DHCP lease time varies according to which server is used. DHCP operates over UDP using ports 67 and 68. DHCP messages from a client to a server are sent to the DHCP server on port 67, on, again, UDP, and then DHCP messages from a server to a client are sent over port 68 UDP. So DHCP address discovery uses 4 different packets: the DHCP discover packet, the offer packet, the request packet, and the acknowledgment packet. When a DHCP client boots up, it performs a standard address discovery, or SAD, to enable it to communicate on the network. After discovery completes successfully, the DHCP client tests its IP address using a duplicate IP address ARP broadcast or gratuitous ARP. So here is a capture of the DHCP discovery sequence. So the discover packet, during the DHCP discovery process, the client broadcasts a discover packet that identifies the client's hardware address. The header contains the source IP address of 0.0.0.0. The preferred address is typically the last address the client used. Next is the offer packet. It's sent by a DHCP server to offer an IP address to the DHCP client. Now, the offer packet includes an IP address that is offered to the client, and sometimes it answers to the requested options in the DHCP discover packet. Now, if the DHCP server can ARP the workstation's MAC address, it sends this packet by unicast to the DHCP client. Otherwise, the entire DHCP discovery sequence will use the broadcast method instead. And here is a capture of a DHCP offer packet, and you can see the IP address of the DHCP server, the IP address lease time, and the subnet mask. Once the offer packet is received, the client can either accept the offer by issuing a DHCP request packet or reject the offer by sending a DHCP decline packet. Typically, a client sends a decline only if it receives more than one offer. For example, if there's more than one DHCP server, as we discussed early on in this video on the subnet, the client's only going to respond to one, and it's going to respond to that one with a request, usually to the first offer it received, and decline to the second and third and any of their subsequent offers it receives. The acknowledgment packet is sent from the server to the client to indicate the completion of the port 4 packet DHCP discovery process. This response contains answers to any of the configuration options requested by the client in the previous request packet. The address renewal process. So when a DHCP client receives an address from a DHCP server, the client also receives a lease time and notes that time that the address was received. The lease time defines how long the client can actually keep that address. When the DHCP client then computes the renewal time and the rebinding time, that's all based on the lease time. So the renewal time, T1, is defined as the time the client takes to renew, or the time the client tries to renew its network address. The renewal packet is unicast directly to the DHCP server. And the default value for T1 is 0.5 times the duration of the lease. So for example, the lease time. This is, so again, 1/2 of the lease time. And then T2 is the rebinding time. That's the time the client begins to broadcast a renewal request for an extended lease time from another DHCP server. DHCP in RFC 2131 defines T2 as 0.875 times the duration of the lease. So here's an example of a DHCP timeline that includes the lease time, so LT, the renewal time, T1, and the rebinding time, T2. And here is a capture of the DHCP renewal, rebinding, and reinitializing process. So although it's not required by the specification, the client should release its address by sending a DHCP release packet to the server. And this is called the DHCP address release process, or just release process. The DHCP release packet is sent over UDP, and the DHCP server doesn't send any acknowledgement. If the client doesn't send a DHCP release packet, the DHCP server automatically releases the address at the lease expiration time. Now, if you haven't configured your clients to send the release packets and you have a limited amount of IP address, this is going to take up valuable IP addressing space if you have to hold every IP address for the full length of the lease. Go back down here to packet structures. So the fields in a DHCP packet, you have your operation code or opcode, or the message type field, the hardware type field, hardware length, hops, transaction ID number, second since boot or seconds elapsed, and flags, the client IP address, your IP address, the server IP address, the gateway or relay agent IP address, client hardware address, server host name, boot file, and DHCP option. Here is an example of the DHCP packet structure. In the DHCP option field, DHCP options are used to expand the data that is included in the DHCP packet. So option 53, message type, it's the only DHCP option that's required in all DHCP packets. It indicates the general purpose of any DHCP message. The DHCP boot sequence uses a few different message types. There's 4 of them. Type 1 is discover, the client to server. Type 2 is offer. Type 3 is request. And type 5 is ACK. And here are more of the message types. So we talked about discover, offer. Request. We didn't discuss decline, but this is here as well as NAC, release, and inform. So broadcast and unicast in DHCP. DHCP clients have to broadcast service requests until they obtain IP addresses. And they also use unicast addressing after they obtain an IP address for a local DHCP server or relay agent. DHCP servers examine DHCP packets coming from clients to determine whether they should use broadcast packets or unicast packets for their responses. As you examine DHC communications, you're going to find a mix of broadcast and unicast addressing. If we look here in broadcast, here's an example of DHCP broadcast and unicast rules. So communications with a DHCP relay agent. The DHCP boot process relies heavily on broadcasts, but most routers do not forward broadcasts. The process also requires a DHCP server or relay agent. DHCP server or relay agent. And the function of a relay agent is typically loaded on a router connected to the segment containing DHCP clients. A relay agent device can be configured with the address of the DHCP server and can communicate using unicast packets directly with that server. The DHCP relay process really works best for a small branch office where it's impractical to locate a DHCP server. You would need a fast and a wide link between the branch office and the location of the server to really prevent transmission slowdowns on the network and delays in address assignment. So again, when you're looking at this, it's really best in situations where you're not going to have the bandwidth or the network access that you need. So here is a example of a network configuration using DHCP relay agent software on a router. And here's the overall DHCP relay communications process. So IPv6 auto-configuration. There's two basic approaches to IPv6 auto-configuration, and that's stateless and stateful. The stateless auto-configuration simply presents the required router configuration information to all comers. DHCP for IPv6 is known as DHCPv6 and is considered stateful auto-configuration because the DHCPv6 server must maintain awareness of the status or state of the pool of available addresses, the presence or absence on the network of permitted clients, and a variety of other parameters. Each method has its advantages and disadvantages, and we're going to talk about those. So the types of IPv6 auto-configuration, the stateless address auto-configuration. So the neighbor discovery protocol allows routers to be configured to present the minimum information a host needs when joining a network link. This is for segments and nodes that support multicasting. And that's in RFC 4862, and it proposes several tools to support stateless auto-configuration of the attached nodes. Now, when we talked about the neighbor discovery protocol, that information includes the network prefix of the segment and the router's own address, and it may include the segment MTU and the preferred number of maximum hops for various routes. And the A and the L flags are set to on for stateless address auto-configuration of nodes. So stateful address auto-configuration, in its basic tasks, DHCPv6 is really a lot like DHCPv4 under IPv4. Both are stateful in terms of configuring hosts. Both rely on dedicated servers that hold databases of information about hosts and their IPs and other configuration parameters. In stateful auto configuration, the router is configured with its A flag set to off and its M flag set to on. That informs the host to obtain its IPv6 address from a DHCPv6 server. You can also combine stateful and stateless address auto configuration. So essentially, stateless auto configuration can be used alone or in conjunction with a method such as IPv6, and then it can be called DHCPv6, and you can call that DHCPv6 stateless. This is a tongue twister. Routers on the local link. When we think about the routers, they can be configured to provide pointers to DHCPv6 servers that can provide only certain other types of network configuration information. And there we're talking DNS server addresses and time server addresses. And the router in this case is configured with the A, L, and O flags set to on and the M flag set to off. So you're essentially combining the two. Remember, in stateless, the A and L flags are set to on, and then in stateful, the A flag is set to off. So you flip that off, turn the M flag to on, and here the M flag is off and the O flag is on. So you just have to be careful about the different flag states between stateful, stateless, and the combination. The router provides the network prefix, and the DHCPv6 server provides the DNS server information for hosts. So here is here's the IPv6 auto configuration address options. So again, when we talk about the combinations of the flags, the combination of a stateless and DHCPv6 is going to result in all flags being on. And then if we can combine Slack with DHCPv6, the M flag is going to be off. So functional states are considered tentative, preferred, or deprecated in terms of an IPv6 auto-configured address. Tentative addresses occur as a node initializes an interface on an IPv6 network segment or link. Valid addresses are usable based on the valid lifetime field in the prefix information option of an RA, or the valid lifetime field in the DHCPv6 IA address option. Preferred addresses are usable based on the preferred lifetime field in the prefix information option of an RA, or the preferred lifetime field in the DHCPv6 IA address option. Deprecated addresses allow nodes to continue to function while they renew the lease on their addresses. And invalid addresses can't be used either as the source or the destination address when the valid lifetime expires. Node interface identifiers, or IDs, for IPv6 addressing are used to ensure that the IPv6 address is unique among all other IPv6 addresses. They're generally 64 bits long. The node interface ID can be construed from different sources, the three most common being the modified EUI64 format, a random number generator to create a 64-bit number, or a cryptographically generated address. After the interface ID has been computed, the process for creating the complete IPv6 address through the various auto configuration option continues. And RFC 4941 added the stipulation that a node using Slack as its auto configuration method has to compute an additional IPv6 address known as the temporary address, and that temporary address is assigned preferred status. This address is used for all outbound communications from the node. So here's an example of the default state in Windows 10 with randomize identifiers enabled. Here's RIs disabled to support modified EUI64. And here is a view with a modified EUI64 IPv6 address on client. So again, we talked about how RFC 4941 states that there's a stipulation saying the node using Slack will compute an additional IPv6 address. That's the temporary address, and it's used for outbound communications. DHCPv6 is defined in RFC 3315, and there's other RFCs 4861, 4862, and other updates to each of those, which define the components that are needed for the process to fully operate. DHCP uses two specific multicast addresses, FF02, 1.2, and FF05, 1.3. And DHCP uses different UDP ports than DHCP in IPv4. So clients that listen for DHCPv6 messages on UDP port 546, and servers and relay agents listen for DHCPv6 messages on UDP port 547. And DHCP unique identifier or DUID methods are DUID LLT, EN, and LL. And there's a bunch of DHCPv6 message types, and these occur between nodes, servers, and relay agents. Here are the DHCPv6 message format fields for messages between nodes and servers. Here is an example of the DHCPv6 message packet structure for messages between nodes and servers. When I said there was numerous message types in DHCPv6, here are the numerous message types for DHCPv6. Here are the DHCPv6 option fields. Here are the DHCPv6 options packet structure. Here is the DHCPv6 option fields. And here are more option fields. And guess what? More option fields. And if you thought there weren't more option fields, here's more option fields. Different this time, relay forward message format fields. and other relay reply message format fields. This is what happens when I'm not talking for a minute or two. And finally, the DHCPv6 message packet structure for messages between relay agents and servers. Now, all these diagrams are in your text, but I figured if you're watching the video, you can pause in each of these sections and look at them. Again, with both the midterm and the final exams, you have full access to these tables, so you don't have to memorize them. Obviously, you always want to memorize the most common types and fields, but it's good to have these on hand as a reference. So the DHCPv6 stateful message exchange, the host sends a router solicitation, and the router replies with a router advertisement, where the A flag is set to off, and the L and M flags are set to on. The host then sends a solicit message, and the DHCPv6 server replies with an advertise message. The host sends a request message, and the DHCPv6 server sends the host a reply message with an IPv6 address, other configuration options, and timer information. In the stateless message exchange, the host sends a router solicitation, and then the router replies with a router advertisement with the AL and O flag set to on and the M flag set to off. The host then sends an information request message, and the DHCPv6 server sends the host a reply message with the other available configuration options. In the DHCPv6 relay message exchange, the host sends a router solicitation, and the router replies with a router advertisement, where the A flag is set to off and the L and M flags are set to on. The host then sends a solicit message, and the router relay forwards solicit message to the server. The DHCPv6 server relay replies to the router with an advertise message, and the router replies with an advertise message to the host. The host then sends a request message, and we're not done. The router relay forwards the request message to the server. The DHCPv6 server relay replies the router with a reply message with the IPv6 address and other options. And finally, the router replies with the reply message to the host. In the IPv6 Autoconfiguration process, here's the basic steps. The node creates an interface ID, and the prefix FF80 is prepended to the interface ID. The node then sends a NS message with its link local address to the destination. If an NA is not received, then the address is considered unique. The host then sends a RS to all routers, multicast addresses FF022, and if an RA is not received, the host starts the stateful autoconfiguration process. Now it's not done. Now if an RA is received, the host is going to examine that message looking for variables and flags. If the L flag is on, the host adds the network prefix to its prefix cache. If the A flag is set to on, then the two IPv6 addresses are created. If the host sends an NS message with its global unicast address as the destination, the host sends an NS message with its global unicast address as the destination. And if an NA is not received, the address is considered unique. Finally, if the M flag is set to on, start the stateful autoconfiguration process to receive an IPv6 address. And then finally, if the O flag is on, start the stateful autoconfiguration process to receive other information such as the DNS server address. And if you want to look at it in a chart, here is the workflow for the full IPv6 address autoconfiguration process. Now, when we talk about Windows and the auto-configuration process in Windows, the basic guidelines for IPv4 is that DHCP is the default configured mechanism for obtaining an IP address, and APIPA is configured to be active by default and will auto-configure an IPv4 address only if the client doesn't receive an IP address from the DHCP server. If you manually configure the address on the machine, both DHCP and APIPA are disabled. Now, with IPv6, link local addresses will be generated using an RNG. If an A flag is set to on and an RA, then the global unicast address is generated. Otherwise, a temporary global unicast address will be generated. The OS sends the RS to any to find any on-link routers. If no RAs are received, the OS starts the stateful address process, and manually configuring an IPv6 address does not disable the IPv6 address autoconfiguration. So on Windows Server 2012 R2, when we talk about scopes for DHCP, the address scopes define a set of addresses that a DHCP server can assign to clients. Super scopes represent a collection of scopes that contain non-consecutive IP addresses. And in IPv6 scopes, you can configure exclusions addresses which are not to be provided to the hosts. So here's an example of IPv4 address pools and exclusions in IPv6 when you're configuring DHCP in Windows Server 2012 R2. As an example, if you want to see here, you can set up a simple DHCP server on a gigabit router you have at home. This is an example using the D-Link AC1750. I've never used this specific router, but you can take pretty much any consumer off-the-shelf router and you can configure this at home using many of the options that we've talked about today. So here's the general network configuration. Here's the D-Link IPv6 configuration. This is a Windows 10 client connected to that D-Link via both IPv4 and IPv6. Here's a connected client screen on the D-Link. And here's a rule editing dialog box. But again, I would encourage you to just go home and try this on your own home router, because odds are it is in there. If it's supplied like an ARIS by a cable company, it's probably buried in advanced options. And even if it's not accessible, you can always find ways to access it. But I would encourage you to play around with this at home. So in summary, DHCP provides a way for computers to obtain usable unique IP addresses and necessary TCP IP configurations. On the administrator's side, DHCP makes it easy to define and manage pools of IP addresses rather than having to go and manually configure every single machine on a network. DHCP origins go back to bootp, as we talked about, and even share some RFCs with bootp. DHCP supports manual or dynamic address allocation, and when a DHCP client starts, it begins the process of DHCP discovery, during which the client can receive an IP address and a lease. And it supports a variety of message types and options. We talked about the various message type 53, so DHCP message options, and it's mandatory for any given DHCP message. DHCP makes use of several message options. Clients supporting IPv6 have new operations for address autoconfiguration. DHCPv6 operates just like DHCP for IPv4 in many respects. DHCPv6 can be used either as a standalone address configuration to clients or in combination with Slack. And finally, the last set of acronyms for the day, DHCPv6 operates with multicast messages since there are no broadcast messages in IPv6.